Okay, for this new section here, we're starting with the second part of chapter 16. Let me adjust my table here so I'm ready to go. Okay, my 3 point check. It's been a while since I've done this. 3 point check for chapter 16, part two. My audio is on, so I'm recording audio. It looks like I'm sharing my screen or the application. And then finally, it looks like I have the recording on. So hopefully, this should be okay. Okay, so moving on, we left off with the last video talking about identifying the base, the acid, the conjugate acid, and the conjugate base. Please notice once again in this type of question, the Bronsted-Lowry base, as I call the BLB, Bronsted-Lowry base, is usually a reactant, okay? And it's the reactant that's accepting the proton. And then the Bronsted-Lowry acid is also a reactant. This is the reactant that is called a reactant because it's giving up the proton. And you will know it by looking at the overall reaction because you have to see what the proton, I'm sorry, the acid becomes to judge it as an acid. Since this ends up, this formula here starts with oxygen bound to two hydrogen, then you end up with oxygen bound to only one hydrogen, and it looks like the whole compound has lost a charge. So essentially, this is judged as the acid, and as for the base, you had carbonate here bound to only one hydrogen with a negative charge. When the transformation was over, you have carbonate now bound to two hydrogens, meaning the carbonate has gained a proton, right? And the overall compound is now neutral. So we're now going to be moving on. And as we move on here, we're now looking at judging acid strength. So for those of you going to organic chemistry, you'll be judging a whole group of acids, right? General acids, or should I say inorganic acids, but mostly organic acids. So this is kind of like the warm-up step. Learning how to judge inorganic acids, the acids that we look at in general chemistry. When it comes to acid strengths and the molecular structure of acids, we want to look at acids in general first. Overall, we're told here you have two categories of acids. We've seen that before. These are the binary acids where you have a hydrogen attached to a nonmetal. Now, in this section here, they use the symbol Y to represent the nonmetal. Then at some point, they make it X. Okay, they're kind of all over the place, but we will follow them, right? We can follow them. So in this case here, Y is the nonmetal. Then down here, the focus is now X. So maybe we should call this X so we're more consistent. Anyway, so you have hydrogen attached to the nonmetal. The nonmetal bears the symbol X. This is a generic nonmetal. It could be sulfur, selenium, tellurium, fluorine, chlorine, bromine, iodine, all those nonmetals, right? And we're told that binary acids, of course, you can see here, binary usually stands for two. You have hydrogen and a nonmetal. Now, the nonmetal, I've already told you what those could be. Most binary acids, about 95% of binary acids, are made up of two different types of elements. There are a few that are called binary that are actually made up of three elements. Okay? For example, hydrocyanic acid or HCN. This is an acid and it's classified as binary because at this point I feel this is me just kind of trying to bridge the gap and say that I feel like chemists were getting tired and saying we're not creating a third category of acids, so this will fit under binary just because it doesn't fit with oxy. Oxy acids have oxygen in them. Okay? So binary don't have oxygen in them, and binary are usually made up of at least two elements, where one of them is hydrogen, the other is the nonmetal. So back to this, your binary acids, a hydrogen attached to a nonmetal. They give you examples here, hydrochloric acid, hydrofluoric acids. And then they're telling you in general, the more polarized the bond, the more acidic the bond. Okay, when you get to organic chemistry, once again, they will talk about acidic bonds or polar bonds. Remember 1411. Before we talked about polarity in a bond, we talked about sharing of electrons, right? So we're going back to 1411, sharing electrons. You share electrons to make a bond. So in 1411, we mentioned hydrogen forming a bond, right? So hydrogen came into the bond, the covalent bond to be exact, because covalent bond is where we share electrons to form the bond. So hydrogen came to the relationship to form the bond with one electron. And I'm going to use here chlorine came to form a bond with the hydrogen with seven valence electrons. So around the chlorine, I'm going to draw seven electrons. You can see right here that essentially in the formation of the covalent bond, the elements forming the bond share not only electrons, but they share unpaired electrons. This is the general definition of covalent bonds. So these unpaired electrons are shared, and since they're shared, they graduate and become bonds. So let me draw that here. The bond here stands for two shared electrons. Okay? We before we talked about polarity in the bond, we assumed non-polar bonds. And remember, polar means difference. And so what we see here is the different ability of the elements due to electronegativity to pull on those electrons. So these electrons are supposed to be shared equally if each of the elements has the same electronegativity. But we learned once again in 1411 that chlorine has a greater ability to pull those shared electrons to itself. It's just one of those natural privileges that chlorine has due to its size. Its size is a lot smaller than hydrogen. For that reason, it is able to pull the shared electrons that were supposed to be shared equally to itself. Okay, the electrons are still shared. They're still equal custody, but the electrons spend more time closer to chlorine. Okay, with that being the case, you have unequal sharing of electrons. So back to the point we're trying to make here, you have more polarized bonds when you have unequally matched elements sharing electrons. Okay, let me try to make this screen slightly larger so I can see what I'm looking at here. Okay, right there. Okay, so moving on. The more polarized the bond, the more acidic the bond. In other words, if you have mismatched elements where one element, like chlorine, is very polar compared to the other, chlorine once again has more advantage over the shared electrons. So the more advantaged the nonmetal is over hydrogen, the more unequally shared the bonding electrons. In that case, it is easier for that bond to break because that bond or the electrons are not holding onto the hydrogen atom very strongly. Okay, so when I was learning this as a student, I was thinking, oh, okay, so bonds hold two elements together. The elements in the bond are held by the bond. If the electrons are spending more time with one element, the bonded electrons are holding on to that element strongly versus the other one that's less electronegative. So I hope I'm not confusing you in the process. Once again, the bond here serves to hold these two elements together. In this case, if this bond is very polar, it is holding on to hydrogen, but it's holding very weakly. Okay. So when this, oh, okay. Hello, Ruby. So when hydrogen chloride gets in water or hydrochloric acid gets in water, this bond easily breaks to release the hydrogen because remember, the bond was polar to begin with, making it very acidic. Okay. So we're being told here if the HX bond is strong, we get a weaker acid. Why? Both elements are being held very strongly. So it's not easy for the hydrogen to get away and get in water. And remember, the very definition of an acid is a chemical that's able to easily give off the hydrogen, or the hydrogen can easily get away from the rest of the compound in water. So if this bond is strong, the hydrogen is being held on very tightly. If this bond is weak, so I'm trying to say this in a different way that is maybe more relatable that you can remember easily. If the bond is strong, the hydrogen is being held tightly. If the bond is weak, the hydrogen is being held loosely, and it's very easy for the hydrogen to be lost or released when the compound gets in water. Okay? So, once again, back to the point we're making here. Stronger bond, hydrogen is being held strongly, so the acid is weak because the acid won't do a very good job at giving up that hydrogen. Okay? So when it comes to comparing acids, we're going to look at the binaries as a group and the oxys as a group. So what I want to do right here, let me move this out of the way. Oh, it won't go away. Oh, great. Anyway, I'm going to move this out of the so I can see it. So when it comes to acidity in general, let me list some acids here and we'll see what they have in common. So we have HF, HCl, HI, HBr, H2S, what else? H2SE. These are all examples of acids. If you look at them, what they have in common is, of course, once again, these are binary acids. You have a hydrogen and a nonmetal because acids tend to have hydrogens and nonmetal at this level that we're defining. Most of your acids have nonmetal attached to hydrogen, correct? With that being the case, when you're looking at the periodic table, which I don't have one right here, most of your nonmetals, I'm going to draw a mock periodic table. Most of your nonmetal are to the top right of the periodic table. Because of that, when you're going across the periodic table from left to right, you tend to encounter more acids on the right. So the rule is acidity increases from left to right because most of your bases are actually here. So I'm going to write here. Your bases are to the left where you have your metals because we mentioned this earlier. Your bases are made up of group 1 and group 2 metal hydroxide, and group 1 and group 2 are somewhere here in the periodic table. Once again, I don't have one right here, so I'm just drawing a mock one. Just, if you can pull one up in your notebook or your notes, whatever, that will really help with this visual, right? Group 1 and group 2 metal hydroxides make your strong bases. Your nonmetals are here, and your nonmetals are ingredients for making acids. So acids tend to be on the top right of the periodic table, majority of them, and then bases tend to be on the left. Okay, that whole column. Okay, so once again, for all acids, whether binary or oxy, this rule applies. When you go from left to right, acidity increases because you encounter more acids. Okay, so when it comes to top to bottom, I want to focus on this right now. Okay, so that was the rule I just stated. When you're going from left to right, you have increase in electronegativity, increase in acidity. When you're going from top to bottom, what we see right here is you actually have increasing acidity because you have decreasing bond strength. So what they're saying here is hydrogen fluoride, this bond here is very strong. And I told you guys before, if the bond is very strong, that just means that both fluorine and hydrogen are being held very strongly. So hydrogen cannot come off very easily because this bond is strong. So going down the group, the bond strength decreases, right? Going down the group, the HI bond is actually very weak. So this hydrogen can come off very easily. And because it can come off very easily, HI is a very strong acid compared to HF. This becomes a weak acid. And once again, this is judged as a weak acid because the strength of the acid is based on the ability of that acid to give off the H ion, the hydrogen ion, the H plus. Okay? So with binary acid, the rule is going from left to right, you have increasing acidity. Going from top to bottom, you have increasing acidity, with this being the most acidic. Okay? So that rule was stated here and here, so we can now move on. When it comes to oxyacid, things get a little bit more complicated. But let me talk about the generic trend before we move on, right? I'll come back to this page right here. Do they have a... No, they don't. Okay. So with oxyacids, just like with binary acids, when you're going from left to right, decreasing acidity is actually... Okay, what do you mean decreasing acidity is strong acid? Decreasing acidity is actually less acidic. So what they're talking about here is decreasing bond strength. I know it's kind of showing on the side. Top to bottom. Oh, you're talking about oxyacids. Okay, sorry. Yeah, I was talking about oxyacid, right? With oxyacids, as you're going down the group, right? You're going down the group, In the binary, H, was it HI? What was the bottommost one? Yes, HI would have given you the strongest acid. With oxy, HIO, when you add in the oxygen, this actually gives you the weakest acid, right? So it's the opposite trend. With the oxy acid, when you're going down the group, you actually encounter the weaker acid. But left and right has the same trend as binary acids. So for all acids, when you're going from left to right, you encounter more acidic acids on the right. But from top to bottom, when you're looking at binary acid, you see your strongest acid on the bottom, the weakest on top. This is only true for binary, right? Weakest acid on top. This works with binary. When you're dealing with oxy, it's the opposite. So you have the strongest on top, strongest acid on top, and this is with oxy, right? And then down here we have the weakest acid on the bottom. Okay. Now, what makes the trend, what flips that trend? Oxygen. That's the thing that's different between the oxy acid and the binary acid. The presence of oxygen flips the trend. This right here is showing you H2SO4. And we're seeing right here that in H2SO4, once again, it boils down to the bond holding the hydrogen. If the bond holding the hydrogen is strong, the hydrogen is being held strongly. So we're looking at this right here. This is sulfuric acid. Acidity happens right here. Oops, I think I pressed the wrong thing. And then right here. So it all depends on how strong this oxygen is holding onto the hydrogen based on the bond strength. Okay. Sulfuric acid is a strong acid. How do we know that? It's one of the six strong acids. Let's review that list real quick. We have HCl, we have HBr, we have HI, we have H2SO4 mentioned right here. We have HNO3, and then we have HClO4. I like to review that often, and I'll be doing that periodically throughout the video because you want to make sure you commit these six to your heart. Any acid outside of these six is weak. Okay. Okay. So moving on. Sulfuric acid is a strong acid. Being a strong acid, it happens to be also diprotic. Diprotic because it has two hydrogens, right? Being a strong acid here, once again, we're talking about the oxy acid. In the oxy acid, the oxygen here is able to hold onto the hydrogen, but it's not doing it very well. That is why this is judged as a strong acid. So what is weakening this bond here and this bond here? It is the other two oxygens right here. These oxygens are electronegative. Both of them are. Back to that electronegative property. Because they're electronegative, they're able to pull the shared electrons, these right here, to themselves. But they're doing that beyond the sulfur. They're pulling these shared electrons to themselves. And then they reach further. I'm like, wow, talk about being an influencer, right? They pull these electrons to themselves. They reach beyond sulfur and pull these electrons to themselves. So you have pulling of shared electrons. Well, when you're pulling electrons, you're actually weakening the bond. Okay? The oxygen pulls the electrons to itself, pulls here. So pulling electrons, this is done by electronegative elements, right? By right here, electronegative elements weakens the bonds. Oops. I need to be mindful of this. Sorry, guys. I'll get used to this eventually. So weakens the bond. Okay. It's all about my hand placement. So going back to this right here, since this oxygen is pulling, it's actually weakening this bond in the end because this pulls, this is also pulling from here. So you have this oxygen pulling, this oxygen pulling, that oxygen pulling, that oxygen pulling. In the end, the bond that suffers the most is the bond holding the hydrogen. And so because it suffers, it becomes very weak, this bond easily breaks, making this a strong acid. Okay, so the more electronegative the element that's attached to oxygen is, the more pulling power it has. Once again, pulling on those shared electrons just weakens the bond. And that's the point I'm trying to make here. That is why the trend is reversed. Okay. The trend is reversed because fluorine will have the greatest power, the greatest pooling power, right? Pooling at that, the bond between the oxygen and the hydrogen. So we see over here with nitric acid, nitrogen once again has a higher electronegativity. So do the oxygens right here. So once again, these are all serving. Starting with this, this is pulling on the shared electrons between these two. Then these ones compound the pooling, including the nitrogen. They are all pulling from the shared electrons between these two, weakening the bond, making this a strong acid. Okay. So I think I've made that point. I'm going to go ahead and move on. So they talk about that here. Now there's a lot more going on with the oxy acid. So we're seeing right here, they're saying once again, the strength of the acid has to do with what's going on between the oxygen and the hydrogen bond, right? And then the electronegative Y element. Once again, Y is the letter being used here to communicate the non-metal. So we're told here the proton is attached to the oxygen atom. The stronger the OH bond, the weaker the acid, because once again, that hydrogen is being held very strongly. The weaker the OH bond, the stronger the acid, because if the bond is weak, that H can come off very easily. Okay? So we're looking here, we're being told the more electronegative the Y atom, the stronger the oxy acid, like I just mentioned. Because even though they wrote it here as HClO, it's really Cl attached to O attached to H. So Cl is pulling once again electrons from the O and then pulling the electrons from the OH bond, making this bond weaker. We don't really care much about the bond strength here. What we care about ultimately is the bond holding on to the hydrogen. So hopefully that makes sense, right? Same thing with H. We care about what this is doing to that bond right there. And we can see right here, the iodine weakens the OH bond by pulling electrons away from it because it is electronegative. Okay. And as we mentioned, acidity of oxyacids decreases down the group, which is the opposite trend as binary. Okay. So this should actually say opposite. Because in binary, it increases down the group, right? What does it say same? This should be opposite. Okay.
So, so
So we're
you're
moving on
saying
from,
so you're saying if
yeah.
the bond breaks, it is considered strong, but if it does not break, it is considered weak.
Yes. Anything that helps that bond easily break creates a stronger acid. Anything that actually makes the bond stronger creates a weaker acid. Now, at this level here, we're not dealing with things that make the bond stronger, but in organic chemistry, you will actually deal with Y parts that actually strengthen this bond. And so at that point, you want to know the things that make the bond stronger and the things that make the bond weaker. At this level here, all we care about is how Y makes the bond weaker, not necessarily the bond stronger. But when you get to organic chemistry, this mystery unfolds even more, and you examine both sides, the Y elements or the rest of the compound that makes the OH bond stronger. And if they make the bond stronger, they just make a weaker acid because the hydrogen is now held in place by a very, very strong bond and it can't come out. But if Y makes that bond weaker, then the hydrogen can come out very easily and that bond can break very easily. Okay. Yeah, so try to learn general chemistry as we're trying to prepare for organic chemistry. Right, it boils down to that weakening of the bond. Okay, good. So the next thing we're talking about here is oxidation number of the central atom. I feel like this one here is a little bit more complex. When you look at oxidation number, the rule does work, but what I like to look at here is instead of oxidation number, I like to look at other factors. But since we're learning oxidation numbers, let me stick with that. We're told here the larger the oxidation number of the central atom, the stronger the acid. Okay? So we're looking at this one right here. We're told carbonic acid is a stronger acid than boric acid. Okay? Now, if you're comparing the number of oxygens, they're the same. You have three oxygens here, you have three oxygens here. When you're comparing the number of hydrogens, you see a difference, right? So this one has got two hydrogens, this has got three. So at that point, you're thinking, well, This could probably be more acidic because there's three hydrogens, but that's not the only problem we see here. The central atom is different. So you have two key differences. While this has more hydrogens, this one here has less hydrogens. The bigger difference and the more significant difference is the central atom. This is boron and this is carbon. So you're told here, if you have this kind of scenario and you're trying to compare the acids, try to figure out the oxidation number of the central atom. Okay. Now you have to go back to 1411 to review the oxidation number rules. So what I'll say for right now is, first of all, do you remember the oxidation number rule? It's probably been a while, right? So what I'm going to do is actually show you kind of a slightly simpler way to remember this, which is look at the snuff, okay? And this might sort of work out to kind of help you out with the oxidation number rule. The central atom in this molecule here, H3BO3, is boron. The central atom here in H2CO3 is carbon. And we mentioned earlier that acidity increases to the right, correct? When the central atom tends to be a greater nonmetal, which in this case it just so works out the oxidation number of carbon here is higher than boron, this creates a more acidic compound. Okay, versus going through the rule of the oxidation number. That will work. I just feel like that takes a longer time. So examine the compound and look at your central atom. Okay, so the central atom rule is higher than even the oxygen and the hydrogen rule. So look at your central atom. Your central atom here, you have a carbon. On the right, you have a boron. You look at the periodic table, the period relationship, and you have carbon that's further right compared to boron. I feel like that goes a little quicker in judging the acidity. Okay. When in doubt, of course, go through the process of figuring out oxidation number. When the central atom has a higher oxidation number, that tends to produce a stronger acid. Okay.
So for this particular example, how it's saying H2CO3, that the only difference between besides the central atom is the amount of hydrogens that are attached. So you're saying because carbon is more electronegative than boron, go with that rule first over the like number of hydrogens or oxygens that are attached to it.
Right. Because with the oxidation numbers that we're looking at here, essentially, as I mentioned, there's so many differences we see right here, right? The oxygens are the same, the hydrogens are different, and so are the central atoms. Sorry, right? These are different. So if the central atoms were both carbon, we will say, let's say this was carbon. Of course, the formula will be different, but just let's say hypothetically that was carbon, that was carbon. The only difference will be the hydrogens, and we'll say the one that has a higher hydrogen count tends to be more acidic. But since you have both a difference in the hydrogen and the central atom, you want to prioritize the central atom difference over the hydrogen. And the one that tends to be sent more to the right in the periodic table, in this case, the one that has a higher oxidation number, okay, will be the one that's more acidic. Okay. And the oxidation number sometimes ties into the charges. So you have to kind of go through and then assign all that stuff. And so, yeah. Let me see if I can do that real quick. So going back to 1411, we learned about oxidation numbers when we're dealing with redox reactions, right? So you had carbon here attached to these oxygens. So in the formula, let's see. It's kind of a long way around, but in the formula here, you need each hydrogen is plus one. Each oxygen is minus two, minus two, minus two. So if you add all the oxygens, you get minus six, right? And then when you look at this positive charge here, you get plus two. So your overall, except for the carbon, your overall is minus four. So based on that, to get a neutral compound, the carbon has to be plus four. So this is reviewing 1411. That's the oxidation number of carbon. And then when it comes to boron, what's the oxidation number? Looking at this formula right here, with the boron, you have three hydrogens, right? Each hydrogen is plus one, plus one, plus one. And then you have three oxygens. Each oxygen is minus two, minus two, minus 2. So then if each oxygen is minus 2 and each hydrogen is plus 1, what must the boron be for you to get a neutral compound? Okay, so you go through this one here and you end up with minus 1, minus 1, minus 1. When you look at the remaining charges being minus 3, boron has to be plus 3 to create a neutral compound. Based on that, boron is plus 3, carbon is plus 4. The one that has a higher oxidation number creates a more acidic compound. Okay, that was, as I said, that was a much longer process, but if you remember the oxidation numbers in 1411, that kind of helps. And the oxidation number sometimes works with the group number, sometimes, not all the time. Okay, in this case, it kind of did work out that way. With boron being in group 3, so plus 3, carbon being in group 4, plus 4. So you just have to figure that part out. Okay. Okay, so now moving on from here, the more hydrogens we have attached to in the oxy acid, the more acidic, right? The more oxygens, the more acidic. So here we're looking at this example here between HClO3 and HClO2. Number of H's are the same, one and one. Number of the identity of the central atoms is the same, Cl and Cl. Number of oxygens are different, right? We have two here, we have three here. Since this has more oxygens, this is going to be a stronger acid. Okay, that means that the bond that holds the hydrogen will be the weakest. Because even though we're trying to use a different method of comparing acidity, the bottom line is the one that's a stronger acid has a weaker OH bond, right? This is the bottom line, the weaker OH bond. Okay, let's see what I have here. I don't know what this is, where this is from. Oh, okay. So we have our six strong acids finally presented here. It was covered in 1411. We're covering it again right now. Then we're told here that a strong acid is a strong electrolyte. And this is very important in lab. We will cover this in lab if we haven't covered it already. Strong electrolyte just means whatever the compound is. In this case, let me look at HCl as an example. When HCl, the molecule, gets in water, if it is a strong acid, it's going to be 100% ionized, meaning that in water, you will not see any HCl molecule intact. All the hydrogens will be completely separate from the chlorine because the bond between the hydrogen and the chlorine is weak. So when it gets in water, the hydrogen will be completely separate from the chlorine, and that is how they will exist in water. Now, you have two ways of showing this picture right here. Can I zoom this in? Wait. Okay, like that. You can show it this way, H plus and Cl minus, or you can show it, I'll make a different container here. You can show it as H3O plus and Cl minus, okay? These are different versions of the same story. H plus and Cl minus just says the hydrogen ion separates from the chloride ion. Here we're saying, yeah, the hydrogen ion separates, but the hydrogen ion combines with the water to make hydronium, okay? Some scientists prefer to communicate at this level, others at this level. It's the same concept, just this one here is more detailed. That's why we say that the H plus is the same thing as the H3O plus. This is just showing you what happens after the H plus gets in water. It combines with water to make hydronium ion. Okay, back to the point I was making. Strong electrolyte means 100% separation between the hydrogen ion and the chloride ion, and we call that ionizing because you're forming the ions, right? Ionizes or ionizing. Okay. Strong acid, 100% ionized. Okay. Here we'll see H3O plus separate from Cl minus. A weak acid is also a weak electrolyte. Okay. Remember, acidity is the ability of a compound that has a hydrogen ion in it to release that hydrogen ion. So if the compound is being judged as weak, that means it's not doing that one thing very well. This acid is only weakly, there's only a small percentage or partial ionization of the acid molecule in water. In this case here, we tend to use an equilibrium to describe the weak acid ionization. Okay? So to show that in a picture form, which later on I'll show you where the slide has an actual picture, a more beautiful one than what I'm drawing right here. But in the picture form, I'm going to use HF. HF, hydrofluoric acid, is an example of a weak acid. So for the most part, the whole molecule remains intact, where the hydrogen ion remains attached to the fluoride ion, right? For the most part. But very little of that molecule actually ionizes, where the hydrogen ion remains separate from the fluoride ion. So to make a point that very little of the molecules actually ionize, I usually just ionize one to communicate very little of these actually ionize. Okay. The rest of them remain intact. So this is an intact molecule of hydrogen or hydrofluoric acid. And to illustrate this in the chemical equation, we'll use a equilibrium arrow because the acid is not doing a very good job. Versus in strong acid, we'll use a one-way arrow. So you have equilibrium arrow versus a one-way arrow with a strong acid. Okay, on the other side of everything, we have the strong base. Once again, with the strong base, you have strength in this chapter is all about completion of the job, right? So you have a compound has a you have a metal hydroxide, and here once again with a strong base, you have a strong electrolyte, meaning in water, the base completely 100% ionizes. So I'm going to give an example here, sodium hydroxide. This will 100% ionizes to form sodium ions and hydroxide ions. So in the container, let me zoom in over here. When you place base molecules in that container with water, the sodium ion completely ionizes and separates from the hydroxide ions. Completely. You would not find, well, I shouldn't say you would not find. Theoretically, it's 100%. When I say theoretically, that means that on paper it's 100%. I mean, in reality, stuff may happen to where the sodium ion reunites with the hydroxide ion, but on paper it is 100% ionized. Okay? With that case, also you have a weak base, which is a weak electrolyte, just like we saw up here. There is some ionization, but it's not very strong. And for the most part, our weak bases, the example here is ammonia. Okay? This will react with water. In doing so, once again, because it's a weak base, you have to use an equilibrium arrow. And then you form ammonium ion and then hydroxide. Okay? Look at that weak base. It didn't even have an OH to begin with, yet it reacts with the water, and then all of a sudden, boom, we have an OH out of nowhere. It does this, but it doesn't do this very well. So in the compound, or sorry, when you take this compound and put it in water, you will have very few ammonium ions and hydroxide ions. The rest of them will just be molecular NH3, remaining separate from the water. Okay? Intact in this form. That's why it's called a weak base. So that's what it says here. This one is still producing OH ion, but it's doing it either by breaking apart or reacting with water. So I used to make up all these stories when I was learning this stuff, just try to understand it. I was like, okay, so this is a molecule that starts off, its identity is weak base, but it knows in its heart it doesn't have an oxygen to release hydroxide, right? The formula doesn't even have a hydroxide in it, but it's able to quote unquote bully water to giving up its hydrogen, and it forces water to release OH. In the process, it gets defined as a weak base because the goal here is that NH3 causes an increase of OH in water, even though the OH came from water, right? I used to be like, wow, molecules on a different level. Anyway, now that we've seen all that, let's go ahead and review these questions right here. In this question, it says without using Ka's, because later on we'll see that Ka can tell us if the acid is weak or strong. When you get to organic chemistry and you're trying to decide if an acid is weaker or stronger and you can't decide because you have conflicting rules, use the Ka because Ka's will tell you objectively which acid is stronger and which one is weaker. Go to your textbooks, go online, and find the Ka for the acid. And we'll learn later on the larger the Ka, the stronger the acid. So when I used to teach organic chemistry, that sometimes the rules were so complicated, and you had these acids where you felt like one acid should have been stronger versus the other, and the rules kind of compete with each other. You have all these things going on. The compounds are very large, and there's so many things going on in the compound. So when in doubt, I was like, let's go look at the Ka, trying to show my students how to rely on the resources to help them answer questions. We looked at the Ka, and then we're able to see, okay, according to the Ka value, the larger the Ka, the stronger the acid. So then that gave us the answer. You could tell as long as the Ka was larger for the acid was stronger. So back to this, we're told to determine the stronger acid without using the K. Well,
Yeah,
sorry,
that's what I
they
was
said
just
the
about to
opposite. My
ask.
bad.
So like for these examples that we're having right here, it doesn't, it's just giving us like the molecules, but it's not giving us like the K. So how do we find Ka when we're not given K?
Actually, they're telling you don't use the Ka. They want you to use the rules we just learned.
Okay.
The periodic, the group, the binary, the oxy.
Okay. Okay. Yeah, that makes sense. Because when I
Right.
saw this, I was just like, wait, how am I gonna do that without it? You know, yeah. Okay.
Right, right. So when you're using the Ka, at that point you have, I would say, you have failed to apply the rules properly, right? The Ka is your last defense, your last act, because you're saying, okay, I try to use the rules are giving me conflicting answer. When I apply this rule, the period rule or the across the period rule, it gives me one acid as stronger. When I use the group rule, it gives me the other acid as stronger. So based on that, I will go ahead and use the Ka. So the Ka is more of your last line of defense. Like you've tried the rules aren't working, then use the Ka. If you jump to the Ka all the time and it's not given to you, you won't be able to answer questions on the exam, right? So since they said don't use the Ka, you're going to use the rules. So looking at these two right here, the number of hydrogens are the same, okay? And they want us to find the weaker acid. The number of hydrogens are the same. And according to that, so since the hydrogens are the same, what is different here is the central atom, sulfur and tellurium. So how are sulfur and tellurium related? And we're looking at binary acids here, right? So we have a binary acid. So we're either looking at a period, across the period relationship, or a group relationship. Okay, so the group relationship, we're seeing that sulfur is above tellurium, right? So we know when we have binary acids, the ones that are further down the group are usually stronger, right? With binary acids. The ones that are further up are usually weaker. Virtue of that, based on that, the acid that has tellurium in it should be stronger. The one that has sulfur in it should be weaker. They want us to identify the weaker. So this is going to be weaker. This is going to be stronger. But they just said identify the weaker one. I just want to do both. So this is a weaker one that we're looking for. So H2S wins as being a weaker acid. Okay. As I said, sometimes they're competing rules. So once again, I'm making this judgment based on the parts of the acid that are different, and that will be the central atom, sulfur versus tellurium. Okay. Now we're looking at oxy acids. I'm going to write here oxy so that my frame of mind can shift. Okay. Yeah, I'm using my iPad and my hands are all over the place, so it's affecting all these things. Okay, so this is an oxy acid. Oxy. Okay, so let's see what is similar and what's different. Same number of oxygens, same number of hydrogens. What is different is the central atom, right? But we're looking at oxy acids, and we know from oxy acids, when you go from left to right, acidity increases. When you go from top to bottom, well, this is with oxy acid, acidity decreases. Okay, so left to right, it increases, top to bottom decreases. Let's see. How are A, S, and P related? Once again, they have a group relationship, right? With AS being on top and P being on the bottom. Oh, sorry, it's the other way around. My mind just trailed off. I was thinking about where do I have a periodic table that I could show right here. I wish I had one right now. It would be hard for me to navigate away from here, but yeah. P on top, AS on the bottom because you have nitrogen, phosphorus, and then, yeah, right there. So based on that, the one that's further down is more acidic, right? So in this case, this one here, I am so distracted right now. The one that's further down is less acidic. So this one here is going to be less acidic. This is what we're looking for. This is weaker acid because I have the rule right here. And that's why I write all of these because sometimes I get distracted. And once I get distracted, I look at this. Yes, thank you. That's a weaker acid. That's what. If you're wondering why I write all these notes, when my mind gets onto something, I get distracted. When I come back, these are supposed to help to guide me. Anyway, yes, it's gonna be the weaker acid. Now between these two, let's see. The hydrogens are the same, central atoms are the same. The difference is the oxygen. So since we have more oxygens here, this is gonna be stronger. But they want the weaker one, so this is gonna be weaker. Very good. So our answer is actually HiO2, H3ASO4. Okay, so my mind is back on this. So we're seeing some more trends here, general trends once again. The stronger an acid is at donating the proton, the weaker its conjugate base is at accepting the proton. Oh, I think there was a homework question that has to do with this. So if you have a strong acid, so this is under the section of Bronsted-Lowry. Remember, acids tend to produce a conjugate base. So you have a weak acid producing a conjugate base, and then you have a weak base producing a conjugate acid. So in this case here, we're told the stronger an acid is at donating a proton. In other words, the stronger the acid is because the acid donates protons. So the stronger acid makes a weaker conjugate base. Okay? So example meaning that if HCl is a strong acid, its conjugate base, Cl minus, is a weak base. Okay? And I didn't really spend a lot of time during lecture talking about this, but let me try to explain to you how I understand this. Remember, the stronger acid is strong because the bond between the hydrogen and the chlorine is weak, right? So this bond breaks up quickly, allowing this hydrochloric acid to give up the hydrogen ion. So we're saying here the strong acid is the stronger acid. Oh, sorry, the stronger an acid is at donating the proton, the weaker its base, its conjugate base is at accepting the proton. So once the chloride ion is formed, the chloride ion actually ends up being more stable, preferring to be a chloride ion. It doesn't actually want to combine with the hydrogen ion to form the acid again. So this is considered a weak base. Because according to Bronsted-Lowry, a base takes in the hydrogen ion. And not only that, a strong base wants to take in the hydrogen ion. If you have a weak base, the weak base doesn't want to take in the hydrogen ion. So the easiest way to remember what I'm saying right now so it's not confusing is strong acids make weak conjugate bases. And that will help you answer your homework problems. Strong acids make weak conjugate base. So if you have, once again, H, if you have HI, this is a strong acid. When you make the conjugate base I minus, this is a weak conjugate base. Okay? That's the bottom line. So that should help you answer more problems. Okay, so moving on. Once again, the higher the oxidation number, the stronger the acid. So we're looking at these two right here. We're being told, I guess this is one question, and this right here is another question. So between these two, the stronger acid is H2SO4. Number one is one of the six strong acids, right? The next thing is it has one more oxygen compared to this. When you're looking at these two here, same thing. This is a stronger acid. Why? It's one of the six strong acids, and then it has an extra oxygen compared to that one. So here, when we're comparing these, we want to look at these three together, and we're being told that in general, acids tend to be more positive. So cations tend to make stronger acids than neutral molecule. Okay. So I write here, acids tend to be more positive. Bases tend to be more negative. Okay? So when you're comparing this trend right here, you can look at this rule I just wrote right here. Acids tend to be more positive, or you can look at the number of hydrogen ions. So there's so many different ways you can approach this. So I'm going to look at the hydrogen ions here, saying I'm looking at what the oxygens are attached to. On the right, my oxygen is attached to one hydrogen. In the middle, two hydrogens. On the left, three hydrogens. Obviously, this is the most acidic, because the hydrogen is attached to the most number of hydrogen ions, right? The other way you can view this is you have a more positive species making an acid. So this one here is most acidic. This one here, if they were asking about basic, this would be most basic. Of course, when I was looking at this as a student, I'm like, of course H3O is acidic. H3O is the very definition of what is an acid, right? It's the H3O species or molecule. And then OH minus, of course, that's basic. OH minus is the very representation of anything that is basic. So that should make sense, right? Now we're looking over here and we're comparing these once again. When you're comparing these three, the one that's most acidic will be this. It has the most number of hydrogens, is the most positive. And then this one here will be the most basic because it's more negative, least number of hydrogens. Okay, but if they're asking you just for the most acidic, look for the one that has the most number of hydrogens. And they tell you, of course, the trend in base is opposite. We already looked at that, so we're good to go. We can continue. Okay, so then here I gave you guys an overview, right? As I said, this chapter has a lot of information. It is interesting, but it's a lot of information. So at some point in the middle of all of this, I said, okay, fine, let's stop and regroup. Okay, when you're trying to figure out acid strengths, besides the periodic table rule, the acid strength when it comes to calculations. So besides the across the period rule, the down the period rule, that helps you. Yes. Yes, very good. I'm glad you're picking up on this. Yes. So acid strength is determined by the following, right? And these are when we're dealing with calculations. Of course, you have the across the period rules, down the group rules, but when you're dealing with the calculations, we tend to determine acid strength by comparing the Ka value. We just said the higher the Ka value, the stronger the acid. Okay. The other thing that we look at is we get the pH. Once you have pH, and if you're taking biology or introductory chemistry classes, the higher the pH, the more basic. The lower the pH, the stronger the acid. But we use the pH number to judge the acidity of the acid. Okay. And then percent ionization. I just mentioned that, right? I said that strong acids ionize 100%. So 100% tells you that you have a strong acid. With that being the case, strong acid, just strong acid. With that being the case, let me erase this right here, strong acid. With that being the case, the higher the percent ionization, the stronger the acid. Okay. And at some point, I kind of mentioned this, that H3O plus is the molecule that we use to communicate acidity. So you can also figure out how acidic something is by directly measuring the amount of H3O plus, because the higher the concentration of H3O plus, the hydronium ion, the stronger the acid. So all the math we're going to be doing from here on is going to center around one of these. We're trying to judge the acid by the Ka value. We're trying to judge the acid by the pH value. We're trying to judge the acid by the percent ionization, or we're trying to judge the acid by the concentration of H3O plus. Okay? Judge, judge, judge. That's what we're doing in chemistry, right? So we know how to pick the right acid for the job. Okay, like I mentioned right here, strong acids have a large Ka value. So at this point, hopefully this sounds like a review because I've said it so many times. Strong acids have a large Ka value. Okay? As I told you guys in class, if I didn't mention this, I want to mention it again. At some point in my life, I have exam anxiety, right? Anxiety period, but in the exam it shows up, and I'll walk in the exam, and right in the middle of the exam I'll just blank. I just forget something, and my mind just is just blank. I'm not connecting to the information I once knew because I'm just panicking. And so I asked my teacher, what is the Ka of this acid? And he looked at me like, why do you need the Ka of the acid? You don't need that. I knew the rule. Even though I panic a lot, I tend to remember information like rules. The rules I remember is just the disconnected information about chemicals. That's the one I tend to forget. So I knew the rule that strong acids have a large Ka value, and then weak acids have a smaller Ka value. So the strong acids Ka value will be bigger than 1. So you see a Ka, like for example, 5.2. If you see an acid with a Ka value that's bigger than 1, that is a strong acid. So sometimes if I wasn't sure if the acid I was looking at was strong or weak, I would look through the whole exam and find the Ka table. If I saw the acid there in the Ka table, most of the time the Ka table will have like 7.5 times 10 power negative 3. If it was this small, it was a weak acid. Now I knew you had to apply it. I just didn't recall the list of 6 strong acids. I know. I know. It was panic. It was the exam anxiety that did that to me. It wasn't that I didn't know it at some point. I just forgot. Anyway, so you want to remember this, right? The bigger the Ka value, when the Ka value is bigger than 1, you're looking at a strong acid. We just said before, strong acids donate practically all their hydrogen atoms. Their bonds are so weak. The bond holding the hydrogen is so weak that you have near 100% of the acid ionizing in water. Okay? We said before, this is a strong electrolyte. So now that sounds like a review, right? So we're told the amount of hydronium ion concentration, these brackets stand for concentration, equal a strong acid. So they should say here, the higher the hydronium ion concentration, then the stronger the acid. I don't know why they wrote it that way. But they said here, essentially, the acid concentration is equal to the hydrogen ion concentration. So once again, to make sense of this right here, because I'm looking at this saying, this doesn't make sense when you look at it this way. But let me show you what happens with HCl. Okay? And I think in class we drew an ice table. I realize this one doesn't have the notes from before. I'm going to add a page right here. Let's look at the acids. So I'm going to look at HCl, aqueous. And for this one here, I'm going to do direct ionization. H plus. You know what? Let me stick with what they're doing. They're saying H3O plus. I'm going to actually go back to how I did it originally. Plus water, liquid, to give us H3O plus plus Cl minus. So I mentioned in class that I write the H3O plus first because I want to remember what species remains behind. Now, as a student, I didn't do that at first, and I used to mess up the formulas. I started doing this, and it really helps a lot. So I'm trying to show you guys this way because I think until you get comfortable with it, this helps you figure out the ion that's over here. Okay, so our acid, let me give you an actual number. Let's say this is zero point 0.1 molar. And I'm going to be using the ice table. I'm trying to remember, have we talked about the ice table at this point? Yes, we have. I'm going to be using the ice table because y'all used it in lab with me yesterday. So I have initial, change, and then end. Remember, strong acids don't have equilibriums because there's no equilibrium arrow here. So for strong acids, this actually stands for the end. Okay? We don't care about the amount of liquid, so we'll block this column right here. Before the acid ionizes, there is zero amount of this ion, zero amount of this ion right here. Now remember, because it's a strong acid, it's gonna 100% ionize, meaning all of the amount of the acid will be processed through in the reaction, right? So since I have zero point 0.1 molar here, I have to use up all zero point 0.1 molar, and that's hold on, all zero point 0.1 molar. And that's what shows that 100% of the formula of the acid got processed in the ionization. We are left with zero. Since the change shows you the stoichiometry, we have a 1 to 1 to 1 to 1 mole ratio. If zero point 0.1 molar acid reacts or ionizes, we make zero point 0.1 molar of the H3O plus, and we make zero point 0.1 molar of the Cl minus. So when you add these two, you get zero point 0.1 molar, zero point 0.1 molar, the end. Okay? Now, back here they said the acid is essentially equal, the acid formula is equal to H plus. I want to say, based on this, the original amount we have for the acid HCl concentration is equal to the H3O plus that is actually made. So this amount that we had originally is equal to the amount of H3O plus made. Versus if you have an ice table and you look at what happens at equilibrium and you look at the number down here at equilibrium, the number here is so much smaller compared to the original acid, right? So since this amount here, zero point 0.1 molar, is equal to this amount here, zero point 0.1 molar, they were able to say back here, the concentration of a strong acid is equal to the concentration of the hydronium ion made, or the hydrogen ion made. That is why this is 100% ionized. I'm trying to say what I've already taught in lecture differently so that you understand. So we have 100% ionization. Okay? Let me see. Once again, we're talking about six strong acids here, HCl, HBr, HI. I'm emphasizing that so you can remember. And then the three binary, the three oxy, HNO3, HClO4, H2SO4. So in our picture here, they're showing you what a strong acid looks like I mentioned before. Strong acids, you have complete separation. Now here they chose to combine the hydrogen and the water, that's fine. Hydronium ion is completely separated from the chloride ion. And we have four particles, right? So four of the hydronium ions, four of the chloride ions. Same here in the picture form. These are the chloride ions right here in green. And the hydronium ions are the positive ones. So some people, I just want to show you guys how to read this stuff. Some people will show the same picture, right? And then just say, since you have four particles each side, they'll just say positive, 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 then negative, 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 negative. So you kind of want to, oh, sorry, you kind of want to know how to interpret these pictures, okay? Because just like you guys, I will watch this and I'm like, wait, I thought we were talking about H3O plus. How do we now skip to the positive? They're trying to say H3O plus, since the acid is more positive, is the positive species, right? And in this case, Cl minus is a negative species. So the positive here represents H3O plus, the negative represents the Cl minus, okay? It's just interpreting the pictures that the scientists draw. Okay, moving on. Weak acid, I already showed you guys this before. With a weak acid, you have an intact molecule here, H and F, and you can see throughout the solution, you have a bunch of intact molecules. Now, they went ahead and ionized too. They can do whatever they want. This is their picture, right? Only two molecules of HF are ionized. The rest of them are intact because this is a weak acid, and hydrofluoric acid is a weak acid. In the molecular form, they show the same thing here. Intact acid molecule. In the solution, you have one, two, three, 4 intact molecules. And then once again over here, you can see we have this one and this one that got ionized. Oh, we have another one here. I didn't see that one. So we have this and this that got ionized, right? And this is a partner. This is a partner. Yeah. Bottom line, weak acid weakly ionizes. So going back here, we're told weak acids donate a small fraction, just a small portion of their hydrogen atoms because the bond between the hydrogen and the fluorine is actually strong. It's not weak. This hydrogen is held strongly, so you can't easily pop it off from the fluorine, right? So if hydrogen is given off, very little of it is actually given off. And here we're told that weak acid molecules do not donate much of their hydrogens in water. For that reason, the concentration of the hydrogen ion in the water is so much less. So these double arrows like this is like saying so or extra are so much less compared to the weak acid concentration. So they're trying to make a point here. Because of that, the weak acid concentration, the one that you started off with, does not equal to the hydrogen ion concentration in solution. Okay? So to try to explain this part here, just like I did earlier, let me go ahead and add a page because I'm trying to make illustrations up as I go. I know what I'm trying to communicate, so I try to find the illustration I can think of in that moment. So let's try to use HF here. We're trying to communicate that weak acids do not 100% ionize. So this is, let's pick a number. Let's say it's 5%. Oh, no, because we have that for something else. Let's pick 7% ionization. I don't want to confuse, right? 7% ionization. So how do we show this is 7% ionized? Hydrogen fluoride, aqueous. I have to do some math. Ruby, I'm glad I have my calculator. Hold on a second. I have to grab it from my bag. Where is my bag? Okay. I need to do some math here. Okay. Okay, HF plus water. Now that we're dealing with a weak acids usually form equilibriums in water, according to Bronsted-Lowry. So we have HF plus water to give us H3O plus and F minus, aqueous, aqueous. Okay? So I'm trying to explain this point right here where they're saying that the weak acid is, when the weak acid gets in water, the amount of H3O plus it produces is not equal to the amount of the weak acid we started off with. So I'm going to stick with the amounts we had here. Remember, we started off with zero point 0.1 of the acid and end up with zero point 0.1 of H3O plus. I'm going to start with zero point 0.1 of the weak acid to make a point here. 0.1 molar weak acid. Once again, we're using the ice table. And I'm trying to make a point here, right? I'm trying to show you how it's 7% ionized. So give me just a moment. Let me do some math real quick. We have 0.1 equals 7. So I'll have to divide by 100. Let's see. 100 divided by 0.1. And then 7 divided by 1,000. Oh, okay. 7 times 10^83. I should have known that. Anyway, so we're having this in the beginning. 0.1 mole of hydrofluoric acid. Then the water column is ignored because it's a liquid, right? So we're looking over here at this part right here. We're looking at the hydronium ion. Before ionization happens, we have 0 amount of hydronium ion, 0 amount of fluoride ion, right? And then we have, due to stoichiometry, ionization, right? Now I don't have this number. Well, I actually just got this number right now, and the number I got was 7.0 times 10 power negative 3. That will be what? 0.007123. Yeah. Let me write it that way. I think it'll be better. So I got here 0.007. Okay. So in other words, if 0.007, if you put 0.1 molar of HF in water, 0.007 of it will actually ionize to produce 0.007 of H3O plus and 0.007 of F minus. Now I just made up these numbers to communicate that this acid only 100, only 7% ionizes, not 100% ionizes. If it ionized 100%, it would be a strong acid. This right here is a weak acid. We're using equilibrium arrows. We're still using the ice table. In this case here, when we look at this, we form 0.007% or 0.007 molar H3O plus. Here you also have 0.007. Over here, I have zero point 0.1 minus 0.007. And so a lot of this molecule here remains intact. So this part here is the amount that doesn't get ionized. Only this part here ionizes. Okay. I don't think I've ever explained it this way before. This is the part that's ionizing. You can see to form the ions. Okay. So when everything is said and done, let's compare the amount of H3O plus that got made versus the amount of the acid we had. So you can see right here, the amount of HF we began with is not equal to the amount of H3O plus at equilibrium, right? This is the amount that we started off with. Back here, the original amount was equal to the amount that was made. Over here, I want to use the same terminology. The amount that we had here originally or initially, I can't spell, originally or initially, the amount we had here was 0.10, and then the amount that was made at equilibrium was 0.007. So you can see they're not equal to each other. This one here is so much less, and that's why we say this is a weak acid. Because for it to be a strong acid, this number here has to match this number. Okay, that's a very different take on what I have been talking about in class. And hopefully, if you're mathematically minded, that would have been of value. If you're not, that was just information. Bottom line, weak acid concentration, the amount you have in the beginning, does not match the amount in solution. The amount of ions released in solution is so much less. Given here examples of weak acids, please notice that this right here is a vinegar or acetic acid. The way we write it in general chemistry is HC2H3O2. I think I mentioned this yesterday. General chemists tend to emphasize the hydrogen first, and then of course you have the rest of the molecule in the oxy acid. Organic chemists tend to emphasize the carbon first and then the hydrogen in the end. So these are both acids, right? I'm showing you the ionizable hydrogen, the hydrogen that gets removed to become an acid, or sometimes called acidic hydrogen. This is the acidic hydrogen that gets removed to form the acid, right? The one I highlighted in yellow. Organic chemists emphasizing the carbon part of the molecule. Inorganic chemists or general chemists emphasizing the hydrogen part of the molecule. Carbon part emphasized, hydrogen part emphasized. But they're both acids, both the same formula. Okay, just written differently. Same thing with this one here. This is the acidic part, not that. I know. It's the part that's attached to the oxygen because the oxygen hydrogen bond is the one that gets weakened. Remember, we mentioned that earlier in the oxy acids? I want you guys to do very well in organic chemistry, right? So, yeah, it's the oxygen hydrogen bond that gets weakened. So, it's really this one that is, yeah, acidic, not that one. It was one of those things that I had to learn because, you get to organic chemistry and you're like, general chemistry was like a whole semester ago. I have slept since then. And so I'm trying to bring in organic chemistry in this class so that by the time you get there, it's almost like a seamless transfer, right? From here to that class. That this is the acidic hydrogen, not that one. So when this gets removed, you end up with HCOO minus. Okay? Yeah, when I was in that class, that I was a little shocked. I was like, wait, what? Not this one? Because I was still thinking like a general chemist versus the organic chemist. Okay. And of course, I wasn't thinking about the OH bond. Who was? This is a new class, new semester. Okay, moving on. Right. So now we're looking at acid strength from the point of view of Ka. We already said The higher the Ka, the stronger the acid. So as we're looking at here, it says acid strength is measured by the size of the equilibrium constant when this reacts with water, when the acid is the one reacting with water. So they're showing this to you here. This is some generic acid. It would be like if you're in a math class and they said the number X, right? This is the acid HA, and chemists like using HA. I call it Ha as your acid. So you have an acid, you write this generic formula here. The acid is aqueous reacting with water that's liquid to form H3O plus and the anion. They're telling you this can be written in two different forms. We talked about this over and over again. You can either be in the team that likes to use the water because you like hydronium, or you can be in team that doesn't like to use the water. Either one of these is fine. It's either or. Bottom line, when you're done with this part here, then you write the Ka. Remember, the Ka is the equilibrium constant where we do product over reactants. I know it's been a while since we started this, but take your product ions, either this and this, or this and this, right? Take your product ions like they did in this case here, and they're trying to tell you that either one is fine. So in this case here, our equilibrium constant for the acid, because the chemical here is the acid, it's going to be H3O plus, right, this product, A minus, leave the water out if you're using this formula here, over, something is happening with my, okay. I have to keep my fingers off my iPad. I feel like something is happening here. But anyway, over HA. There, right? So you're either writing it this way because you use the equation that has the water in, or you're writing it this way because you use the second equation. But either one is fine. They're telling you they're equal to each other. But yeah, for the most part, we tend to stick with this way because most books in America use H3O for the hydronium ion to communicate the acidic ion versus H plus. So I tend to stick with that one more. But when I was back at home, I learned it this way before college. Okay. Oh, I have a whole blank page. So I was mentioning before to you guys that when I forgot what was the strong acid, what was weak, I came over here. Okay. Not to this particular page, but to a page that was similar to this. And if the Ka of the acid was less than 1, I knew immediately that was a weak acid. I mean, I could have just memorized the 6 strong acids, but I told you guys before, I am not good at memorizing stuff. Like I learned stuff eventually, but the process by which I quote unquote memorize stuff is
Focus
not really
one.
memorizing. Okay, so yeah, once again, go through here all the Ka's, and the Ka shows you that the when the Ka is less than 1, you're looking at a weak acid. So all of these are weak acids. You could also once again remember the 6 strong acids, whatever is not of the 6 strong acid list is a weak acid. So looking at this right now, here we can say real quick, these are all less than 1, right? Because they're less than 1, they're all weak acids, weak acids, weak acids, weak acids. Now that we've actually learned about the Ka and how Ka relates to the acid strength, we can now say that we kind of just answer the question, right? The following is a list of weak acids and their Ka values. So it says which acid given above is the strongest. We said before, the larger the Ka, the stronger the acid. So the largest Ka here looks like it's this last one here. It's a whole number. Remember, when it's power -4, there are fewer zeros. Power -10 is a bunch of zeros, right? So it's like, yeah, it's gonna be just in case you're wondering, 4.5. Move the decimal to the left, 4 spots, right? 1, 2, 3, 4. That's where the decimal goes. Fill in zeros. 1, 2, 3, 4. And so you're comparing this number versus the rest of them. Of course, this one here, you're going to move the decimal 10 times and fill in the zeros. Move the decimal 7 times, fill in the zeros. Move the decimal 8 times, fill in the zeros. Bottom line, this is going to be, even though they're all weak acids, this is going to be the strongest of the weak acid. Strongest. So that will be HNO2. And they say for that weak acid, write the Ka expression for the strongest acid. Okay, so HNO2 aqueous plus water liquid to give you H3O plus aqueous plus NO2 minus aqueous. Okay, Ka for this acid is equal to H3O plus, ooh, let me write over here out of that spot, NO2 minus over HNO2. Yeah, I'm about to stop this video in a little bit, but this is a Ka value. And then now we're going to move on. Let me finish up the autoionization of water, and then I'll start with a new lesson. I'll say where I'm going to start the new lesson. Oh, right here. So this is going to be the end of this video. Okay. Okay. With the autoionization of water, what we're saying here is essentially water is neutral. Okay. So I remember learning this in biology in basic chemistry classes, pre-general chemistry, pre-college, or even pre-high school. Water is neutral. Why wasn't water neutral? It had a pH of 7. When they were talking about water being neutral, the context was the pH value, right? So the pH value, you have a pH that goes from 0 to 7, then from above 7 to 14. So anything between, well, above 7 to 14, this was basic pH, with 14 being the most basic, and then below 7 to 0, that was acidic pH, with 0 being the most acidic. So if you get burned or exposed to an acid that has pH of 0, that's very caustic and it will burn, really, really burn if it falls on your skin. Okay? So we're told water is amphoteric because it can act as an acid or a base. For the most part, it's neutral, right? So when it comes to Arrhenius' definition, water is neutral. When it comes to Bronsted Lowry, that's when he expands the role of water. We're seeing water in different lights. We're told here water can be acid, water can be base. It depends on what water is reacting with. So how can water be an acid and a base when we just said it was neutral? Because it contains both acid ions and base ions. We see that in something called the autoionization of water, where water where a water molecule, liquid, reacts with itself, liquid, to produce two ions, aqueous and aqueous. Okay? So the water is called autoionization because the water naturally just reacts with itself to produce ions. But this happens automatically. Okay? And the ions that are produced are the acid ions and the base ions. Okay. So just like we did before, we're gonna be writing the equilibrium constant, but this is gonna be the water equilibrium constant. Since the focus of the equilibrium is the water chemical, we'll use the equilibrium symbol Kw for the constant because it's equilibrium constant for water, right? So our equilibrium constant for water expression will be our products of a product, the product of the product ion concentration. I know it's a lot to say. H3O plus multiplied by OH minus, right? Divide by the reactants? No, these do not make it into the equilibrium expression because they are liquid. Equilibrium expression only takes in aqueous and gas phase chemicals, not liquids or solids. Okay, so here we get our Kw equation from the autoionization of water. Okay, now from here we're told that I'm going to show you this later, but since Kw actually has a specific value right here, I'm showing you right now, as 1.00 times 10 power negative 14 at room temperature, then we notice that in water, the concentration of hydronium ion equal the concentration of hydroxide ion. Okay, so a different way of looking at this is, remember, H3O plus hydronium ion communicates the presence of an acid. You have a lot of it, a strong acid. Very little of it, a weak acid. Hydroxide ion communicates the presence of a base. So we're told in water we have both presences. That's not really a word, right? Both presence. Okay, we have the presence of both the acid and the base, and they're equally matched. So water is neither an acid nor a base, but when necessary, it can channel the acid ion, and when necessary, it can channel the base ion, and that is usually shown in the Bronsted-Lowry equation. It does have equal amounts of acid and base. So in water, the acid strength and the base strength is matched. So we have a draw, and that's why we can say water is neutral because the hydronium ion concentration matches the hydroxide ion concentration. It's a draw. Okay. I like using sports analogy for a lot of sports that I don't even know. So since we know what the KW value is, they're telling you here that I want to erase and write right here and not pull up a whole new page. Bear with me. You can rewind and look at that part. So what they're saying is, since you know that KW is equal to the hydronium ion times the hydroxide ion, you can actually solve for these values. You know they're equal, right, in water. So KW is 1.100 times 10 power negative 14. These are equal to each other. So just make it, how, yeah, they're equal. So how about you write like this, H3O plus, and then replace the OH minus with another H3O plus, just because they're equal to each other, right? We just said in water, H3O plus is equal to OH minus. If they're equal to each other, we can actually replace it in the equation to solve for this, right? So, oh, this is supposed to be negative 14. So this becomes H3O plus squared, and this becomes 1.00 times 10 power negative 14. So to find the H3O plus, take the square root of that, that gets rid of that, takes the square root of that, you end up with H3O plus being equal to 1.00 times 10 power negative 7. Since they're equal to each other, H3O plus will be equal to this, and so will OH minus. And when you multiply these two, you get this number we started off with. Okay? So they tell you all aqueous solutions contain both H3O plus and OH minus, but in water, these amounts are equal to each other. And they are equal to this value right here. Okay? So now we can move on. Okay. So I'm close to finishing up this chapter here, but I want to mention something. In all solutions, as it says right here, in all solutions that contain water or all aqueous solutions, apparently we have not been paying attention to this. Those solutions contain both hydronium ion, acid causing ion, and hydroxide ion, base causing ions, right? But if you have a neutral solution, it doesn't have to be water, a solution that has water, then we expect for the acid ion to equal the base ion because it's neutral, it's a draw. And each of them has to be or has to have this value. But if you have an acidic solution, while both ions are present, the one that's more dominant or in greater amounts will be the acidic ion. And they're telling you here the acidic ion or acidic amount is greater, much greater. When they say this, it's just greater. When they say this and this is much greater. When they say this and this and this, it's like, are you kidding me? Is the other one even present? They're trying to say this is so extra, right? They're trying to communicate it's so much greater, significantly greater that we have to notice that it matters. Okay? So this is greater. And then in basic solutions, the base ion is so much greater. It's significantly greater that we have to notice. It makes a difference. Of course, the acidic solution, the pH is smaller and the pH is larger. Okay? Next one we're looking at is K. It says using KW calculations, calculate the OH at 28 degrees. We're going to use the same equation we had before to solve for this. So I'm going to go ahead and finish this part here and then wrap up this video. I'm close to the end. Close to the end. I'm going to write all three right here. KW is equal to H3O plus and then OH minus. So what I'm going to do to make this go quicker, I'll replace KW with the actual value, 1 times 10 power negative 14. Okay? So in this case, they gave us what H3O plus was in each case. We're trying to find OH minus and figure out what is the more dominant species. Is it H3O plus or OH minus? Because we're having a constant competition, right? Unless we have a draw. So we're going to try to figure out, since we have H3O plus, we need to find out OH minus so we can see which is more dominant. So for that, I have to rearrange the equation. To find OH minus, I need to take 1 times 10 power negative 14 over H3O plus. Okay? So I'm going to be using this equation over and over again. For part A, the OH minus amount is equal to 1 times 10 power negative 14 divided by 7.5 times 10 power negative 5. Okay, let me turn this on. Open parentheses 1 exponent negative 14 divided by 7.5 exponent negative 5. Okay, I'm missing a parentheses here. So let me insert that. Oh, okay, that works. So I end up getting 1.33 times 10 power negative 10. Okay, since this one is going to have more zeros, it will end up being smaller than that. So I'm comparing this amount here. So what I'm doing here now is looking at H3O plus, which I had what? 7.5 times 10 power negative 5 molar versus OH minus, which I had 1.33 times 10 power negative 10 molar. When you compare these two, this is obviously larger because it's going to have fewer zeros in the front. This is going to be smaller because it will have more zeros in the front. So this wins. This is going to be more acidic. So I can judge the first one as A for acidic. Let me check and see if they got it. Yep. Did they say acidic? Yes, they did. Moving on to the next one. I'm going to do this way for all three of them. The next one I have 1 times 10 power negative 14 divided by the second one here, 1.5 times 10 power negative 9. And our answer is, let me go back to this one here. I'm trying to go, okay. So now I'm going to use the equation here. Let me delete. It's like I'm ready using my calculator. 1.5, 1.5, and then exponent negative 9. So 1.5 times 10 power negative 9. And I get 6.667 times 10 power negative 6. So when I'm comparing the two solutions, let's see what we have. For my H3O plus, I have 1.5 times 10 power negative 9, right? This amount here. For my OH minus, I have 6.667 times 10 power negative 6. This has more zeros, so this is going to be smaller in amount compared to the other one. So this dominates. This is going to be B for basic, because we got more basic representation present than we do have acid, right? Okay. Last one real quick. This last one is actually very quick. This is where we talk about question design, not knocking the author or the president or the designer of the questions, but sometimes their trends are so predictable. Let's see how this goes. We got KW on top. Now we're working on this one here. 1 times 10 power negative 7. Okay. So we end up with 1 times 10 power negative 7. So our acid ion amount is 1 times 10 power negative 7 molar. Our base amount is 1 times 10 power negative 7 molar. They're equally matched. It's a draw. It's neutral. Really? I'm sorry. They're trying to give you the experience so you can get experiences, the acid experience or the acid question experience, the base question experience, and then the neutral question experience. Basic solution, neutral solution, the end. So this is the end of chapter 16, part 2. Okay, I'll be back for the third part.